maybe next week I will be away. I'm not sure which day I will be away. So we might need to decide some replacement. If we cannot meet physically, then we have to do at night online. Okay. Maybe we'll decide later. Okay, no? Yeah. Hello? Okay. Can Steven join now? Yeah. I think it's the right check now. Yeah. Okay. Let's look at let's do some warm up. Look at the ring homomorphism from integer. Okay, to R. Okay, to any ring R. What kind of a map you can define? So is Z a ring or not? Z is a ring, right? You can add, you can multiply, and then under addition is a additive abelian group. Okay, but there's no multiplicative inverse. Okay, but that's fine. That's okay for the ring. And for our ring, considering the commutative ring. Okay, so the multiplication must be commutative. Okay, so it works in integer, right? 2 times 3 is equals to 3 times 2. Okay, you always get 6. So what kind of map you can define? Yeah. First of all, you need to satisfy the ring homomorphism. Okay, ring homomorphism. What are the property of ring homomorphisms? Yeah. Ring homomorphism. What property ring homomorphism need to satisfy? Hmm? You know? Don't know. Ginseng? Ring homomorphism. E? Sorry, again, louder a bit. Equals to? Yes. Okay, this is one of them. There are 3 of them, 2 more. Consort. VAB equals to VA times VB for all AB in the ring. And then one more. Okay, V1 equals to 1, correct. So that means what? You need to send the 1 inside your Z to the 1 inside the ring R. Okay, sorry. This one should be 1. Okay. So you need to send the 1 in the integer to the multiplicative identity in the ring. Okay. And then this pretty much define everything. Why? Z is a cyclic. Okay. It's a cyclic group. Right. It is generated by 1. Okay. So how do you define for 2, 3, 4, 5, 6, 7, 8, 9, 10? How to define? Huh? How to define for 2, for example? 2 is what? 2 is equal to 1 plus 1. But P of 1 plus 1 equals to what? P1 plus P1. Okay, so you are doing addition 1 plus 1 in R. Okay, so for positive Z, okay, for positive Z, for positive Z, it is sent to 1 plus 1 to the n times. Okay, to the n times. Okay. So inside integer, what else? What number you have? I already settled everything greater than 0. What else do you have? Yes, it's more than 0. Okay. So how do you decide for number that are negative? Hmm? How do you decide this number? Right? Additive inverse. Why? Why? Hmm? Additive inverse of who? Sorry? Of 1? Additive inverse of 1? What's the additive inverse for 1? Minus 1. So do you send every negative integer to minus 1? No, right? So what should you do? Additive inverse of who? Minus of phi of the absolute value of m. Right or not? Sense? Okay. So why is this true? Why is this true? So when you define, you need to check your group homomorphism, right? Okay. So let's say we start with this positive n here. Okay. What do we get? Phi of minus n plus n is equals to what? P of 0. Okay. But a ring homomorphism is the same kind of group homomorphism. Okay. You must sense 0 to 0. Okay. But on the other hand, what do you get? On the other hand, I can split phi minus n plus n into phi of minus n plus phi of n. Okay. Then I can take inverse on both sides. So phi of minus n equals to minus of phi n. Look front. Okay. Yeah. Phi of minus n equals to minus phi n. Is that alright? Okay. Does it make sense? Okay, so this decide what is the minus positive integer should go to. Okay? Minus of the phi of the uh, value of n. We still have 0, right? We settle for greater 0, less than 0. Okay, we still have 0. So we should send 0 to where? 0. Because it has to be a homomorphism. Okay, and then this is the only way to do it. Okay, this is the only way. So if you ever want to consider an integer sitting in every ring, this is how it sits. You have to send 1 to 1, okay, and then all the positive number to 1 plus 1 n times. Okay. For negative number, just phi, just negative, just send it to the negative of phi of the absolute value. Okay, make sense? Okay. So for example, okay, maybe you wonder, okay, what is, how about negative 2, right? What does negative 2 looks like? So negative 2 should send to negative of phi of the absolute value of negative 2. What is this? This is just phi of 2. But I tell you how to send phi of 2. So where should phi of 2 go? Phi of 2 should go to 1 plus 1 2 times. Okay, so there are 2 of them here. Make sense? Okay, so you just send to the inverse of this. Not that I write 1 plus 1 here, I cannot say it is 2 because I don't know what is the 1 in my ring. I also don't know what's the addition in my ring. Look at the last assignment. Your ring is a what? What's the example you consider? It's a set, right? Set. So what's the multiplicative identity there? And then what's addition there? Is some taking some difference of set, right? Okay. Not that I just can write 1 plus 1. I cannot write it as 2. Because 1 plus 1 in different ring means different things. Make sense? Okay, that's why my notation here, just keep it as 1 plus 1 n times. Okay? Yeah, depend on your ring, the 1 will change, and then the operation will change. Okay or not? Okay. Yeah. All right. Let's continue. So last time we stopped at fields, right? So what's the property of field? What are the only ideals in field? And the zero ideal. Why? Because every non-zero element are invertible. Okay, so if you're gonna generate your ideal, all of them will have multiplicative inverse. And then you're gonna generate one. Once you have one inside your ideal, you can generate the whole ring. Right or not? Okay. So once you have one inside your ideal, you will generate the whole ring. Okay. And then if I have a ring, okay, I found that there's exactly only zero ideal and unique ideal. What can I infer about this ring? Huh? If I have a ring, there's only two ideals inside there, zero ideal and a unique ideal. So what can I infer about that ring? It is a field. Okay. So if and only if. Okay, if and only if. The statement. All right, let's continue. So next, we will still look at the ideals in the ring. Integers. Okay, let's look at the ideals in the integers. What do you think? What are the ideals in the integers here? Can you classify them or not? And what are the ring? What are the ideals in the integers? Any number, and then try and generate the ideal. Okay, what do you get? Huh? Any idea? Take your favorite number in the integer. What's the favorite number in the integer you like? Huh? 64. Okay, 64. Hey, how do I know your mind one? 64. Okay, let's take 64. So in every class, you pick 64, is it? Yes. So you take 64. Okay, you want to generate the ideal. How to generate the ideal? Huh? Take all the multiplication of R with 64, where your R is living in the ring. What's our ring? Our ring is Z. Okay, so these are the multiple of 64. But this one is principal ideal. Okay, we can do something else. Pick one more, maybe. But don't so pick one. 89. Okay, let's pick 89. So what's the ideal generated by 64 and 89? These are what? These are linear combination of 64 and 89 in the uh integer. So R1 times 64 plus R2 times 89. Okay, where R1, R2 are in the Z. Okay. But 89 is what kind of number? Okay, it's a prime number here. There's a prime number. But what's about prime here? It can generate whole numbers. How? What do you mean by generate whole number? Whole integer? How? How? Reverse Euclidean algorithm. Okay, good, very good. So, so what does it's not called reverse Euclidean algorithm, right? There's a name for it. Huh? Bezout algorithm? Is it? Identity. I think they are similar. I mean, similar names. Okay, use the Bezout, B-E-Z-O-U-T, right? Yeah, Bezout algorithm or the inverse Euclidean algorithm. What does the inverse Euclidean algorithm tells you? If the two numbers are coprime, okay, so the Bezout identity or the hey, why my iPad today like this? The inverse Euclidean algorithm. So for all m and n for prime, there's this R and S in Z. M and N also for prime in Z, such that what? R times N plus X times N equals to 1. Okay? Meaning what? Meaning you already consider all the possible linear combination, right? Meaning this 1 is also inside your ideal. So if 1 is inside our ideal means what? It is what? This ideal is equal to the whole ring. Okay, actually, in fact, this is the whole Z. Okay, so if you have 61 and 89 together, you get the whole thing. Right? You get the whole thing back. In other words, this 60, the ideal generated by 64 and 89 is a unique ideal. You can find one element that generates this ideal here. From 1, can you generate 64 now? How? 64 times 1, correct? 89, how to get from 1? 89 times 1, correct or not? 1, okay? It says that the unit ideal is equal to 64, the ideal generated by 64 and 89, right? So that means I can use 64 and 81 to generate 1. How? Use the Bezout identity. Okay, you can find the R and X. So how to find this R and X? You can actually find it. Go and do your Euclidean algorithm. Okay, on 89 and 64. Okay, and then inverse it. That's why we call it an inverse Euclidean algorithm. Find 1 in the linear combination of 64 and 89. Then you can find your R and X that build your 1. Make sense or not? Okay, go and try and do it. Okay, don't just listen to what I say. You should do it. I do it already, so I know. Okay, so you have to do it. Okay, actually, one point from this Bezout identity here is, what is this one here? What is this one here? Why this one? Why this one here appears? Can I change this one to anything else or not? GCD. Okay, in general. Okay, so in general, what? Let me this down. Okay, in general, what happens? So in general, for all mn in Z, okay, I don't need call prime, that exists R and S in Z, such that Rm plus Sn equals to the GCD of Mn. Okay, so this is true in general. So meaning what? Meaning all the ideals in the ring of integers are the subgroup of subgroups of Z. Okay, just generate by one element. And these are the principal ideals. Okay? So if you take any integer or any ideal in the rings that's not the unit ideal or the zero ideal, you can find the GCD between these numbers. And then this GCD will generate the ideal. Just use one GCD to build all of them. Okay? Yeah, no. So the proof is, okay, I don't want to write down. It's a bit troublesome. Okay, I will include the proof inside the whole proof inside the lecture notes. But do you get the idea now? You get the idea? So if you have an ideal in Z, okay, go and test your Bazooka identity. Find the GCD between those numbers. Okay, then if all these numbers have the same GCD, then that GCD will generate the whole ideal. Okay. If it is one, then you are happy already because you can immediately stop. Because one will get everything else. Okay. So like what I said last time, so we want to generalize this situation to a polynomial ring. Okay, so we will, let's see, are we going to prove this? Let's see, I will give the statement first. So it's the same in the polynomial ring. So especially the ring of polynomial rings over a field. So the statement is every ideal in the ring fx of polynomial in one variable x. I think the magnetic field is too strong. One variable x over a field, okay, is principal ideal. Okay. So just now we find GCD, right? GCD of two numbers. But now what should the be the generators of this principal ideal? Can you imagine? GCD of polynomial. So what should be that thing? What should be that thing? Should be that thing. What's the GCD between two? Remember last time we divide by what? What's the division we do in polynomial ring? We divide by what kind of? Yeah, we divide by a monic polynomial. Okay, so a non zero ideal I in fx is actually generated by the unique monic polynomial. Okay, so this unique polynomial will play a role like the GCD in integer. Okay, that it contains. Okay or not? Okay. We see the proof of this. This proof is quite classical. First of all, any question on this statement first? Do you know what is happening before proving? So if you take any ideal in a polynomial ring over field, again, it is a principal ideal. So you can find one thing that generates the ideal. And then what's that thing? That thing is the unique monic polynomial of the lowest degree inside the ideal. Okay, if you can find this unique monic polynomial of the lowest degree, then this polynomial will generate your ideal. You get it? Okay. Let's prove this actually. Let's prove this. So since this is true for every ideal, right? Okay. Then you need to take any ideal, okay? Any one of the ideal. Just take one of them. Okay. And what can we suppose? Suppose that I is not the zero ideal. Okay. If not, we are done because zero is the unique monic polynomial. Suppose I is not the zero ideal. If not, we are done. Okay, so now there's one thing we need to introduce, right? We need to get our monic polynomial up. So let f be a monic polynomial with the minimum degree, okay, with the smallest degree inside my ideal. Okay. So why can we always do this? When I say let, right, I can pick. Why can I pick like this? Why can I make sure my leading coefficient is always 1? Where's the coefficient live in? Sorry? Field. So meaning I can invert every non-zero element. Okay. So I can find the smallest degree. If it doesn't has leading coefficient 1, we can divide everything by the leading coefficient. Right? We can, or in other words, I can multiply by the inverse. Okay. We can always do this because our coefficient live in field. Okay, live in a field. F. All right. So we want to show that I is exactly the ideal generated by F. Okay, so this is our goal. Okay, no? So one direction is easy. Which direction? Whenever you see this, right, you should immediately split this statement into two. I need to show left to right, right to left. So which one is easier? Which inclusion is easier? Which inclusion is easier? I contain F, right? So any multiple of F should be contained in I because I is an ideal. So we can see that it is easy to see the principal ideal generated by F is a subset of I. Again, because I is an ideal. F is in the ideal. So multiple of F should be in the ideal, right? Because I is closed undertaking multiplication. Okay, with the ring elements. Make sense? Okay, now. Simple. Okay. Yeah, you like this? Huh? Tired. It's okay. We all are tired. right? So we have to word. Okay, word. Yeah, no choice. Okay or not? Okay. How about the other direction? Next, we show that I is a subset of F. Okay, so go back to the set theoretic definition here. What do I have to show? I need to take any element in F and then show you that it is in the set in the principal ideal generated by F. Meaning what? I need to be able to write the elements as a multiple of F. Okay or not? Okay. So what should I do? So I take G in I. Okay. We want to show that G equals to Q prime F. Okay, for some Q prime in the ring. Okay, what trick we can use here? What's the method we can use here to prove? Remember last time how we proved the kernel of some homomorphism is generated by the polynomial. So what's the trick here? I want to do division. So by the division with remainder, what do I get actually? I can divide the G using the F, okay, plus some remainder here, okay, plus some remainder. So plus some remainder, where the remainder should have degree less than with degree of R less than the degree of F. Correct or not? Okay. But at the same time, R equals to G minus QF. I claim that we have a contradiction here. Why? Sorry? R also? R is also in I, correct. So I claim that there's a contradiction here. Why? Why is there a contradiction if R is in I? It's the degree problem here. Remember that F is the smallest degree that we pick in I. But now I generate a smaller degree, a function with smaller degree in I. So this contradicts the minimality of the degree of F. Okay or not? Does everyone get why this thing is in I? First of all, F is in I, G is in I pick one. A linear combination of things in I is still in I. Okay, so R is in I. But R has a degree less than the degree of F. But I already say, I pick the minimal degree function, which is F. So there's no more or smaller degree F inside my function, inside my ideal. So this is the contradiction. Okay, so but I consider which contradicts the minimality of degree F. Okay, so this is the contradiction. So this means what? This means that R have to be 0. Okay, if R had to be 0, then we are done. Then G is divisible by F. There's no remainder. Make sense? Okay. This is a very classical proof. Okay, the minimality, contradiction of minimality. So This question here says that the unique, I only say one, right? I only pick one monic polynomial just now. Why is it unique? Okay, uniqueness proof. So at the start from this course, I already told you, it's very important for maths. There's two things you want to take care. One is existence. One is uniqueness. Okay. But typically uniqueness is the one that's easier to prove. Okay, without incurring this kind of complicated argument here. So let's see. So suppose, so how about uniqueness here? Why is it unique? Right, just now I simply pick one. I just simply pick. Why is it unique? Right, it doesn't make sense. Okay, so suppose F1, F2, okay, are two monic polynomials with the lowest degree. What can we do about them? What can I do about them? What can you do about them? I can take the difference. I can take the difference, right? Okay. Consider F1 minus F2. What is F1 minus F2? They are monic. Okay, the leading coefficient is the same. So if you take the difference, what do you get? You get a polynomial with, yes, with a lower degree. With a lower degree. Lower degree than the degree of F1, which is equal to the degree of F2. Again, a contradiction because F1, F2 has the lowest degree already. You cannot get lower than it. Okay. This, so no contradiction yet, no contradiction yet. So consider this is then F1 minus F2 must be 0. Okay. Otherwise, you would have a lower degree polynomial. You will have okay, I should put like this. You will have a polynomial F1 minus F2, okay, which is, okay, no, which, just a polynomial of degree of positive degree, which is strictly less than the degree of F1 and F2. Okay, then you have a contradiction. Okay, make sense or not? Yes. Yes. So I haven't explained it. So otherwise, I explain it. Next sentence, I explain it. If it is not 0, then you have a polynomial F1 minus F2 with positive degree, okay, which is less than the degree of F1 and F2, which is a contradiction. Because the degree of F1, F2 is the minimal out of all the the polynomial inside my ideal. Okay or not? Yeah. So sometimes the argument lies before. Sometimes the argument lies after. So when you read one statement, right, make sure you read it, how to say? Thank you. Oh, okay. So you need to read the argument before and after. Okay. You cannot just read it and start here. You can go beyond a bit. Okay. Because yeah, that's how people put things. Some people like to explain everything and then tell you the conclusion. Some people like to tell you the conclusion and then tell you why. So these are the two attitude you will see in a proof writing. Okay. So each time you stuck at a place, go up a bit, go down a bit. F1 and F2 are monic, yes, correct. So because we suppose that F1 and F2 are two monics, a polynomial of lowest degree in I. This is the lowest one I can find. These two. Okay. So general statement for uniqueness is you suppose there are two things with the same property, and then show that they are the same. Okay. Once I got F1 minus F2 equals 0, that means F1 equals to F2. Okay. So every uniqueness you do like this. I take the two things with the same property, and then I show that they are equal. That's all. Okay, you see, I didn't incur any other extra condition here other than the minimality. Okay. Or taking the difference. That's all. Yes. Define zero polynomial to be. What do you mean by undefined? Uh, let me think. Because zero is inside every. Let me think. What should I say about it? So first of all, the degree of a polynomial must be non-negative. Right? Not. And then what's the degree? Yeah, you can understand. So I guess yeah, you can understand. So yeah. And also zero is in every ideal. Zero is inside every ideal. So you can always find zero in every ideal. It's like the empty set is a, okay, let me think. Yeah, empty set is an element of every set, right? Yes. It's vigorously true. Vigorously true. Hmm? No. Zero is inside my ring. So if I take zero, multiply with the generators in my ideal, I get zero. Zero is in my ring. Okay or not? I still haven't gone into 11.4. Okay. 对，王哥，yeah. Okay or not? Okay. Uh, yeah, let me quickly go through, finish this part. Then we have to reach our target today. Okay, example, how we use this example here. So let P be a morphism from the polynomial ring over rational to the complex. Okay, for example, let's say I just send x to cube root 2. Maybe a bit fancy here, but anyway. What's the kernel of this map? What's the kernel of this map? What's the kernel of this map? What's the kernel of this map here? What's the thing get sent to 0 under this map? X minus cube. X minus 2, 3, yeah, cube root of 2. So what's the polynomial that can get sent to 0? S cube minus 2. Correct. S cube minus 2. What does phi does to S cube minus 2? Right. U times Px cubed to Px, and then the whole thing cubed because it's a ring homomorphism. And then usually if I don't tell you what to do with coefficient, it just fix it. Okay, you just imagine there's a inclusion little phi from this coefficient ring to the domain, called the codomain. Okay, so it becomes 2. Here we get cube root 2 to the cube minus 2, which is 2 minus 2, which is 0. Okay. And then just now we see that every ideal in the ring, in the polynomial ring of one variable over a field is a principal ideal. Okay. In particular, this principal ideal is generated by the unique monic polynomial of lowest degree. Okay. So this ring here, Qx, is Q a field or not? Is Q a field? No. Are all the non-zero elements invertible or not? Yes, right. Yes, right. This is exactly how we build the rational number. We want to invert everything in my integer. Like 2, half, 3, the inverse of 3 is 1/3. Okay, so on. Right. So in particular, this kernel here is an ideal. So this kernel have to generate by one element. What is that single element it generates? It used to generate. Yes, this polynomial here. Okay, this is the smallest degree polynomial that will get sense to 0. You can try smaller degree. For example, consider ax squared plus bx plus c. Okay, if you send this across to c, can you get 0 or not by any mean? Can or not? What do you get here? You get a of cube root 2 to the, okay, actually it's 2 to the over 3 plus b to the 2 to the 1/3 plus c. Can you substitute any a, b, c so that this thing is 0? Can you find non-zero polynomial that gets evaluated to 0? Can or not? Can you fit any a, b, c such that this thing is 0? You can, only 0. A, b, c equals 0. But when a, b, c are all 0, that means what? You send 0 to 0. That's always true. Okay, so there's no lower degree polynomial than s cubed minus 2 gets sent to 0. So that means the smallest degree that gets sent to 0, the smallest degree polynomial that gets sent to 0 is s cubed minus 2. And then by the theorems, it tells you that the ideal must be generated by this one. Make sense? Yes, Zhou. Why? Why? Very good question. So where is ABC? Where should this ABC live? This ABC should live in, wait, let me move something so that I can write it. Very good question. This is a very good question. So wait, let me move. Make sure I write it better. Where where should this coefficient lies in for polynomial? This number should be rational, right? Where A, B, C are rational. Sorry.
This is another form, writing form of rational.
Oh, this is my lecturer teaching me one, so I just keep it like this one.
Okay.
Yeah, rational. My rational look like this. Sorry. Rational.
So this kind of rational.
I mean, no. I mean, for latex it's standard. This for writing. So. Okay, this is my rational. So these are rational. So can you find rational when you multiply with irrational and then can you solve this? I mean, so let me think how to say this. Let me think. Okay, so one thing I want to say is rational. Let me think. So I wanted to say this 2 to the 2 over 3, 2 to the 1 over 3, and 1 are linearly independent. How to say this? Cannot solve meaning they are linearly independent, correct? No? So, but this linearly independent is the coefficient is in rational. It's not in real. It's not in real. It's in rational. Okay. So let me think how to say it. Okay, you cannot find a rational such that you multiply to 2 to the 1 over 3 to get 2 to the 2 over 3. Or get 1. Okay. Proof. How to prove? How to prove? No, I mean, how to say? I mean, how to use linear algebra? Linear algebra word in R, real. Now we are doing something in. Okay, this one I think a bit out of topic, but we take a break and then between this break I can think about it. Others can go and break because I want to continue after 412. So we have 10 minutes to settle this. If we want to settle this. Okay, let's use this 10 minutes to settle this. So why it doesn't exist? Okay, let me just reduce. Maybe we just reduce question to this. Okay, why there's no B in Q such that B times 2 equals to 1. Okay, I know how to solve. I know how to solve. Okay, first of all, let's say I cannot go from irrational. Okay. Let me do it more generally. So why there doesn't exist B in Q such that A in this one throw away this. Hey, not that this one a bit different. I go in this way. This one is throw away. And then the other way is quotient. Okay, so take note. So algebra got this constant here. So why you don't if you they don't exist rational such that there's such that for all irrational that B times the irrational equals to 1. For example, we prove that 1 is linearly independent with rational first. Okay, no? Because if this is true, otherwise, then I can write A equals to 1 over B. Okay, then this contradiction. Okay, contradict. A is irrational because irrational you cannot write as A over B. The square root thing is a bit complicated, I think. Square root thing is a bit complicated. So why root 3 over 2 and root root 3 over 2 square and root 2 are linearly independent over where? Over Q. Okay, why? 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 Sorry? Mm.
Then we can just extract one 2 root 3 out, and then
Say again. Say again. A, yeah, okay, if A times 3 square root 2, cube root 2 square plus B times cube root 2 equals to 0. You cancel one.
cancel the 2
Oh, okay, you want to use inverse. Anything? Okay, so suppose this is true. Okay, suppose this is true. Then we can multiply the inverse of root 2 on both sides. That's right? Okay, so I multiply inverse of root 2 on both sides. So where is this operation live in? I'm living in the real. I'm actually living in the real now. Okay, I'm living in the real now, but I didn't change the condition on my A and B. Where should I get A and then using the previous things we know that, okay, since that cube root 2 and 1 linearly independent over Q, A and B must be equal to 0. I think this works. Yeah. Okay or not? But later we will also see these linearly independent, right? Using polynomial ring. Later we'll see it using polynomial ring. Now we see it using root, but later we'll see it using polynomial ring. In polynomial ring, then it's easier to see because x squared, x cubed, we know they are linearly independent. Yeah. Yes. What do you mean variable in the polynomial ring? You mean substitution? This x? Yeah. What do you mean by choice? If A and B must be inside a ring, then how about the x? X is just something extra. Something extra. We call it an intermediate or a variable or a placeholder. Anything? What do you mean by anything? X is just x. X is just x. For this example here, we want it to be cube root 2. Then we substitute cube root 2 to every polynomial with x. So we just study a general polynomial in x. Yep. No. There's no domain of that. No. So that's why last time we talked about a polynomial ring or a formal power series. These polynomials are formal. These are not function. Just formal thing. Okay. Just anything. It's an intermediate. It's a placeholder. Yes. Law of composition of X. No relation. Sorry, wait. Sorry, say again. X squared is defined as X times X. Why is it multiply? No. I mean, how to say this? Wait, let me think. Okay, so like this. So the power of X is just defined to be like X dot X dot X 3 times minus 2. Okay, and then you ask what is the law of composition here? It's just X dot X dot X. That's all. Yeah. That's the right way to say it. Yeah. It's just yeah.
So the plus and so the plus multiplication and addition.
Second.
The dot or plus inside the polynomial is just a very general sum of multiplication and addition we define on the polynomial ring.
It's just a formal plus, if you want to say so. Formal plus. Yeah, formal plus.
Always confuse on X. It also belongs to the game itself, to the ring itself.
Oh, it's not. It's definitely not belong to the ring itself, first of all. Okay, because we want to create a new variable. Yeah. X is not part of the. Okay, so let me give you another statement. So if X is in R, okay, then R adjoin X, we call it adjoin this square bracket. This polynomial ring is what? It's really just R. Okay, no? You can show the inclusion. Left to right, right to left. Okay, one way is easy, right? R definitely, it is easy to see that R is a subset of R join X. But the other direction is still easy because R is closed under multiplication. Okay. Also, it's also in R because R is closed under addition and multiplication. Yeah, so the question you asked me just now is about why polynomial ring is a ring. Yeah, why polynomial ring is a ring? You need to define the multiplication and the addition. Okay, how do you define them? Actually, you are defined by coefficient wise. Yeah, I think I briefly mentioned this. Okay. So that's why it acts like x plus x equals to 2x. Why? You are not adding x, you are adding the coefficient of x together. 1 plus 1. Okay, not there's a 2x there. There's 2x, but 1 plus 1 equals. But it is intuitive, right? Because x bar x should be 2x. Yeah. Yeah, formally, we are defining addition of the coefficient. Okay? Of the monomial. Make sense or not? Yeah, so yeah, at the start. Yeah. Yeah. Mm-hmm.
我会拿那个 polynomial，那写这个 polynomial 是 degree less than 他们两个。
Yeah，
所以我这边就讲它出问题了。
怎么出问题？
我是有 conclusion 讲这两个是这两个是最小的这两个都是
对对，
我现在找了一个更小的，也在那个 ideal 里面，
对，
这 contradiction 掉。
但是它有一个情况是它等于0嘛，对不对？你减的时候，你一定会拿到一个情况
对，所以我想这个零会出现是因为我们 define
没有0，这就会出现是因为你的算法。假设我 polynomial 最小的是 x2，另外一个找到也是 x2嘞，它减出来肯定有0的，对不对？因为这两个都符合我一开始的条件嘛，拿两个出来，
所以
我没有讲拿两个不一样的出来哦。
谁是讲 zero polynomial？
是一个 possible 的 computation 来 result
degree 不是零。
没有，是说它是其中一个答案嘛？那个 polynomial zero polynomial 是其中一个答案。
没有我把 zero polynomial 当做 degree 是0，所以我直接没有那个0的变成。可是因为我们这边 define 的方向 zero polynomial 是 undefined
如果0有什么情况？你说如果0有什么问题？
因为我把 zero polynomial 当做成一个 zero constant 那个，
然后有什么问题呢？
它 degree 就是0，
然后有什么问题？问题出现在
因为你现在 f1 减 f2 是一个 polynomial 小过前面两个这个 polynomial 小过前面两个也在 ideal 里面
但是你要知道，如果一个 ideal generated by 0的话，0 是 0，
就是 zero ideal，
0 ideal，
就全部都是0。
对，这样你就没有其他东西来，就没有 positive degree 的完全在。本来其中一个原因我们 define 它 undefined 是因为0会活在所有的 ideal。你看，如果那个 positive degree fixed size x square principal ideal generated by x square， 现在 x 这个 polynomial 就找不到了，在这个 ideal 里面就找不到，对不对？它最小是 x square 了。
因为里面有 x 不算
因为除非我 consider 跑那个什么 adjoin 它的 inverse 进去的话，就可以了，没有的话就不能。
然后你的 maximum ideal
我们会讲，但是principal ideal maximum ideal，maximum ideal 是说 principal ideal 只是说它 generate by 一个东西，我们应该要讨论 prime ideal，maximum 先还是 prime 先，其中一个先了过后 ，maximum ideal 是说再比它大的 ideal 就是整个 whole ring， 它是那个比 ring 小一点的那个 ideal。
所以虽然我们这边讲的 principal ideal 其实
是 generate by 一个东西，可能有些 principal ideal 是 maximum ideal， 你只要再加多一点东西进去，它就是整个 ring 了。maximum ideal 就是说，它有一步就去 ring 了。
比方书本那种概念就对了。
为什么呢？你发现？
再拿一个maximum ring， 然后
maximum ring，
maximum ideal， 然后我现在如果找到一个比它还要大的一个 polynomial，
就是
比比较大的 polynomial， 然后也generate
不是这样想他的想法是你有一个 maximum ideal， 你只要再加一个东西进去，它就变成 ring 了。加 extra 东西，
这边加一个 element 进去。
要 generate 吗？不然你只乘，肯定还在活在里面的嘛。是 ideal 嘛，肯定你是要 加的加进去。你一动它，它就变大了，它就 reach 到整个 ring。
所以 maximum ideal 的 generate 的比怎么？
不一定啊 ，depend。
可是 principal ideal 是一个吧？
啊，对对对对
啊
，things yeah。maximum maximum ideal 是 principal 它是 about 那个 generator，maximum 是 about 那个 ideal 本身。prime 又有一个叫 prime。
generator 都是 prime
不是 prime 的，它会符合像 prime number 的特定，但是它本身的 property，我们在讲就是说 A、B 如果在 I 里面 ，A 或 B 一定要其中一个要在 I， 不可以两个都是外面混进来。Hello, testing. Okay, so let's quickly go through these two points here. Maybe the technique is not too important. Hello, ready or not? Ready? Okay. So we quickly finish these 2 points in 11.1.3, then we go to 11.4. Okay, there's 2 points here. So there's one lemma here. So if f is a monic integer polynomial, so meaning it's a monic, and then all the other coefficients are integer, and then you have another integer polynomial. If you can divide f by g, in the rational, that means you also can divide f by g in the integer polynomial. This result, maybe you think that it's kind of obvious, but it's kind of important. Okay, very important if you go to a Galois theory. Go to AA2. Okay? Yeah, this means what? When you do division in rational, actually you don't need to divide. Don't need to use element in the rational to help you to do the division. Okay, you just need integer to do the division. Okay, this is the accent of this lemma. There's a proof here. You can have a look. But the accent here is you do division by integer, because integer you should think maybe I will get 2/3, right? Maybe you'll get 2/3. But if it is divisible in QX, then it is divisible in ZX. You don't need to use 2/3. It is divisible. You can try. Okay, you can try. Okay, can make sense. This theorem more important in AA2 because it's not our focus here. But the result of this corollary is kind of important. This corollary here. So this means what? If my polynomial ring, is over a field, and you have 2 elements f and g. Okay, should I point out to see how I read? So let's take any 2 f and g, and they are not both 0. Okay, you don't take both of them are 0. Then their greatest common divisor, just now we talked about this roughly, is exactly the unique monic polynomial that generates the ideal. Okay, and this is the property. And then you should recall that this property is really the same as the GCD of 2 integers. You can go and flip back your textbook. Okay, these 4 properties appear in the integer. Okay, now. So this is what we call a principal ideal domain. Let's I think hopefully we'll get to it next week or 2 weeks after. So it's the ring. You take any ideal, all the ideal are just principal ideal. What is what we call principal ideal domain? Domain is another property. Okay. Principal ideal domain. PID, which we call it. So Z is a PID. And polynomial ring is also a PID. But I haven't tell you what's D. So make sure you come to lecture, I'll tell you what's D. What's D? You guys watch One Piece or not? No, okay, it's okay. What is the PID? I mean the domain. Integer domain. I'll teach you next time what's the integer domain. Okay. So far we only touch PI, principal ideal. Okay. We'll see what the domain is. Okay. Okay, next we should go to this important things, quotient rings. Also your assignment about quotient rings. So really, quotient group quotient rings, these are the accents of this course. Okay, you must learn what is the quotient groups or quotient rings here. So similarly, it's the same argument here. So what's the theorem we have? So what do you quotient by in a group? Normal subgroup. Okay, so here normal subgroup is the kernel of some homomorphism, right? So the kernel of a ring homomorphism satisfy the property of ideal. Okay, so now we take ideal. So let I be an ideal of a ring R. Okay, then what do I do with this ideal here? Cut. Okay, or we quotient. Okay, quotient by. So there exists a ring structure on the set R quotient I, or we call it R bar. Okay, so how to understand this R bar? Because your ring is also a group. Okay, it's also a group. So this you can consider as an additive coset. Additive coset. Additive coset of I such that the map, the canonical map. Okay, remember what's that canonical map? You sense the element to where? To its coset. Okay, to its coset. It's a ring homomorphism. And the kernel here is just the I. Okay, this part here is still the same with a group. Okay, the the group. Okay, no. Any question? So how to prove this? How to prove this? No. I mean, what you need to do first. Let's decide what you need to do first. I think we won't write the proof, but we need to decide what we need to do. What should we do? So there exists. So meaning you need to define, right? You need to define how you add the coset, how you multiply the coset, and then all the ring property, how many you check? Distributivity law, right? You need to find the multiplicative identity, additive identity. Okay, all you need to define and find it out. Okay, and it is the unique one. So meaning you need to define two such two ring structure and then show that they are the same. Okay, unique one. Okay or not? The whole proof is in the textbook. So if you want to have a look, it's similar to the one how we showed it for group. Okay. Okay or not? Is it okay? Yeah, maybe not too enlightening if I prove it here, and it's quite tedious. But maybe I need to tell you how they multiply and add. Okay, let's tell you how they multiply and add. And then you need to verify why it works. Okay or not? So I need to at least tell you how they add. So how you add two cosets together? Okay, how do you add two cosets together? How do I define this addition here? Any idea? How to add this two cosets here? Addition is a subgroup, right? So in the quotient of a group, how do you add? How do you multiply? How do you compose? Yeah, representative add up. So what do you get? A plus B plus I. Okay. So you send to this coset here. Okay. And how about multiplication? I have A plus I multiply. Okay, maybe use this times B plus I. What should I get? FB plus I. Okay. But you can see that, for example, you can construct an example. It is not always true that if you take two coset like this, you multiply together, you immediately get another coset. But what you can see is the inclusion is always true. This is always true. Okay. You don't get the whole coset product. I think it's in your assignment. You prove that when ij is a coset, ij is a ideal. Okay. When you multiply two ideal, you don't always get an ideal. Okay, but you live in some ideal. But this is the unique ideal it live in, so it's okay. I pick this one. Okay. Okay, this is a technicality here. Okay or not? The other direction is not. I mean, yeah. So when you multiply two ideal together, you don't always get a ideal. Okay. Then you need to check all the properties or distributivity. What's the multiplicative identity, additive identity, and so on. Okay, you need to check all those. We won't check it here. Then what's the next thing? What's the next thing after this? What's the next thing? We have the first isomorphism theorem. We also have first isomorphism theorem for group. So maybe I just show it. I don't want to write it out because it's the same property here. Okay, so yeah. So what's the mapping property of quotient ring? Okay, so you have the surjective homomorphism of ring now, right? And then you need to check what's the kernel of this surjective homomorphism. And then this kernel is an ideal. So you can quotient up your domain with this ideal here. And then it should be isomorphic to the image. Okay. Yeah.
What is the name of A plus I? In group we call that coset. Then what do you call it?
Yeah. Also coset. Also coset. Wait, let me think. Let me check. Is it coset here? Yeah, we call it coset, additive coset. Yeah.
Additive coset.
Yeah, because ring there's no coset, right? So it's an additive coset. Yeah. Because multiplication might not be a group.
So additive coset partition the whole ring, right?
Yes, that's right. That's right. That's right. That's right. That's right. Should be true. Yeah. Should be true. Is it true? Be true. True. Let me think. Yeah. Coset. So you mean if an ideal, does ideal, let me think. Does ideal is the ideal equivalent class or equivalence? Can I define an equivalence relation? Is it additive? I don't know. Is it reflexive? Surely reflexive, right? If it is it transitive? to some relation, and then yeah, it is transitive. Is it reflexive? It is reflexive. Yeah, it is an equivalence relation. I think the truth feel like wrong, but okay. Let's put it. Let me think about it. Huh? No, not conjecture. I think it's some. I'm not sure there's some technicality or not. I cannot rule out, so I cannot confirm. So you ask whether the ideal generates. I mean, ideal quotient the ring or not, right? I mean, the ideal partition the rings. Okay. The identity concept. Yeah, partition the ring. One part I don't sure is about the ring structure. So does the multiplicative structure affect the partition or not? It should. I mean, from here, right? From this first isomorphism theorem here. If you have an isomorphism here, that means you should partition your set. You should partition your set. You should partition your ring. Yeah. You should partition your ring. You should partition your ring. Yeah, with the additive concept. You should. Otherwise, this concept gets sent to one image. The other concept gets sent to the other image. But these two sets have intersection. So how go to where that thing? Okay. Yeah. Similarly, we also have the correspondence theorem. This correspondence theorem is similar. Okay. So there's a bijective correspondence between the ideal in the domain and the ideal in the codomain. So the ideal in the domain must contain the kernel. Okay, like last time, must contain the kernel of the morphism. Okay. Okay or not? So there's a correspondence between ideals contain the kernel of the map with the ideal in the codomain. But make sure that you start with a surjective or a ring homomorphism so that you can talk about all the ideal in the codomain. Need to be surjective first. But there's some very important remark here. Let's see. So how to construct it? So if you have an ideal, okay, of your domain, and that ideal contain the kernel, what is the corresponding ideal? You just apply your map. So like last time, you have a subgroup, okay? You apply group homomorphism. It is the image of a subgroup is still a subgroup. So same here. Image of an ideal is still an ideal. Okay, try and show it. Image of an ideal is an ideal. And how to go backward? If you have an ideal in the codomain, you just use your surjective homomorphism to pull it back. Okay, look at the inverse image. Still form an ideal. Like last time, inverse image of a subgroup is also a subgroup. Okay, it's the same. Can see the similarity or not? Try and prove it. You need to practice. Okay. But the key thing is here. If the ideal, okay, I of R correspond to the another ideal in R here, we can consider the domain quotient out by I and the codomain quotient out by the corresponding I. And then these two are isomorphic. Okay, this is very important. This is the thing that we're going to use later or in your assignment. Keep using this. So you have this correspondent property, and then I can take the domain quotient out by the ideal contains the kernel, and then I can take the codomain quotient out by the ideal. Okay, these two ideal have correspondent. Then these two rings are naturally isomorphic. Make sense or not? You should think that the domain ring and the codomain ring might be something very different. Okay, but I have a surjective map that put them together. Okay. Obviously, these two are not isomorphic, right? Because one is bigger than the other. But if I quotient out by this I, correspondent I, they become isomorphic. Somehow they have the same things, and then they behave the same way. Make sense or not? I will show you example later. Okay, but does everyone get the idea of this statement here? Okay. Okay, I think we won't prove this because half of it is the same as the group version, and then the other there's some technicality to play with. Okay, so let's go to example then. Let's go to example. Go to example. Okay, example. Let phi be a map from the two variables polynomial ring to one variable polynomial ring. Okay, be a ring homomorphism. Okay, how should I define this ring homomorphism? I just need to tell you where the variables go. Okay, where the generators go. X to t, y to t squared. Okay, I fix like this. Is this surjective or not? Yes, right. Because I know what's the pre-image of t. Pre-image of coefficient, constant, or the scalar. So what's the element here? These are the linear combination of power of t. So you should tell me where the coefficient goes, all right? Like where should what's the pre-image of C complex number?
C.
Just the exact R, okay? Okay, because we usually look at the inclusion, okay, inclusion. So the inclusion here is row, so I should write it here. I include my coefficient C into CT, like this. Usually, if I don't mention, I don't alter the scalar. Okay, if I don't mention, it just sit inside CT. This is what we call inclusion. Okay, so this map is surjective, right? So since it is surjective, meaning there's some kernel here. But what's the kernel? What is this kernel here? Yeah. Sorry, s square minus y. Okay. And last time someone asked me, if I put s square minus y here, can I write y minus x square? Can or not? Is the two ideals the same? Can I write y minus x square? Is this two ideal the same or not? Why the same? I can multiply -1 to the generators to get the other generators. Okay or not? -1 is inside my ring. Okay. Okay, so this is my kernel here. Okay. So by the correspondence theorem says what? All the ideal in the domain that contains this kernel here correspond bijectively to the ideal in the codomain. Okay. So what are the ideals in CT? Yeah? Can I classify all the ideal in CT or not? CT is a polynomial ring in what? In C. C is a field, right? Because you can find inverse for every non-zero element. So the ideals are C is a field, but CT is not a field. right? T is not invertible. It is a polynomial ring over a field. So meaning it is a P, I, E, right? Every ideals, just now what did we conclude? Every ideal in the polynomial rings in one variable X over a field, okay, is principal ideal. Okay, every ideal inside such polynomial ring is a principal ideal. Okay, so all the ideal in a CT must be principal. Okay, meaning it generated by what? Generated by what? Yeah, what's that one element? How do we describe it last time? What's that one element? How do we describe it last time? Yes, monic polynomial with the lowest degree. Okay, so we can take so in particular J is generated by one PT. Okay, where PT is monic. Okay. So in this case here, what? So then by correspondence theorem, theorems, what do we have? How do we describe all the ideal that are in bijective correspondent to J? So how should we describe every ideal I of the domain that contains the kernel? What is it form? What's the form of it? So just now we say that if I have an ideal in the codomain, I can take the inverse. I can hit the inverse. So what's the inverse of PT? What's the inverse of PT? What's the inverse of PT? I'll go back here. Precise. I have a polynomial PT in the codomain. Okay, what's the inverse here? For example, t squared, t cube, t cube. You just take px is fine, right? Okay, px is fine. Maybe there's other inverse, but px works. Okay, so the ideal is generated by px and also the kernel. Okay, also the kernel. Okay, no? Does it make sense? Does it make sense? This one seems a bit easier than the group because last time, remember you do the example of S3, you need to go and check all the pre-mesh. But now the ideal here is generated by something. So you just need to check the generator. You see, I only check the generator. I only pull the generator back. Again, PT. What's the inverse of PT? PX? Okay. I just see the generators. Let's look at more example. Okay, let's look at more example. So let's look at second example. So let's look at all the ideals. Okay, identify the ideals in CT shown out by t squared minus 1. Okay, what are the ideals here? Okay, how to study the ideals here? And think about it. How can you use the correspondence theorem? Can you build a surjective map or not? Can you build a surjective map or not? You are taking quotient, right? Meaning you are killing it. You are sending the ideals to 0. So can you make a map that sends the ideal to 0? Huh? Can you map a map that sends the ideal to 0? Can you define a map that sends the ideal to 0? Huh? Can you define a map that sends the ideal to 0? Sorry? Square root x plus 1. What do you mean? So you mean you want to do something like what we did just now, is it? Like, for example, E from CT to CT, sending like X to, sorry, sending, wait, let me think. So it's E going to, also not true, right? You cannot do this. Yeah, you cannot do this. Yep.
Another stuff another doing.
Yeah. So actually, you can form a map from CT to this ring, right? Okay, by killing. Exactly, you set it by kernel with a kernel of phi equals to t squared minus 1. Just do this. Okay. I just send this ideal to 0. And then what I do to the rest, I send t to t. What is this actually? This is the canonical map. This is actually the canonical map. This is exactly the canonical map. Okay. This is exactly what the canonical map do. Okay. If you cannot imagine this ring, you should imagine the group. You should imagine the group. All right. So under this map here, how do we study the ideals? How do we study the ideals? Which side we know better? Which side do we know better? The right side, right? Because this is again the polynomial ring over field, right? So all the ideal there are principal. Okay, all the ideal there are principal. Okay. So all the ideal on the right hand side correspond to all the ideals here that contains the kernel. Okay, and then it is principal. Yeah. Okay, so let me write down. So let I be an ideal in CT, okay, that contain kernel P, okay. Like before, we know what? We know that I must be principal. Okay, I must be principal. Principal. And in particular, it's generated by what? Which is generated by what? Generated by what? Principal ideal of the polynomial ring generated by what? By what? Huh? Monic. Okay, again, monic polynomial. Okay, let's call it maybe F. Okay, F. Monic polynomial F. Okay, it's generated by monic polynomial F. But think about it. Think about it. Inside this ideal, I contain the kernel. But kernel generated by what? Just now, our kernel generated by what? Our kernel generated by what? T squared plus 1. Okay, our kernel generated by T squared minus 1. But this principal ideal contains T squared minus 1 generated by F. So meaning what? T squared minus 1 must be divisible by F. Right? Because I said this ideal is generated by F. And then T squared minus 1 is in there. Okay. Then but T squared minus 1 is in I. So F divide T squared minus 1. So what are the monic divisor of T squared minus 1 here? What things divide T squared minus 1? T squared minus 1 can be written as what? T minus 1 times T plus 1. And then 1 also divided. So there are how many of them? 4 of them, okay? Because you can be, F can be T minus 1, F can be T plus 1, F can be 1, F can be T squared minus 1. Okay, so there are exactly 4 of them. Make sense or not? So now the ring problem suddenly come back to this factorization. Make sense or not? Okay, so you need to know how to do factorization. Very important. Okay, so factorization, F divide this. So therefore what? Therefore, there are 4 ideals containing kernel T in CT, okay, which in bijective correspondence the 4 to the 4 ideals in the quotient ring. Okay, how are we quotient it? So T squared minus 1. Okay, so what are these ideal then? What are these coset? How does this coset look like? Okay, how does this coset look like? How does this coset look like? So one of them is obviously the ideal T squared minus 1. And then, yes, 1 plus T squared minus 1, T minus 1 plus T squared minus 1, and T plus 1 plus T squared minus 1. Right? These are the 4 cosets. Okay, no? So there are 4 cosets here. Just now we said that quotient ring is a ring. So I can put ring structure on these 4 things. How I multiply these 4 cosets together. How I add these 4 cosets together. Okay, then you can apply what we have just now. Okay, this ring here, this quotient ring here have 4 elements. Okay, this is a 4-element ring. I can multiply the coset together. I can add the coset together by what we do just now. A plus I plus B plus I equals to A plus B plus I. So 1 plus I plus T plus minus 1 plus I, what do I get? I get T plus I, but any T plus I here, no? No T plus I here, right? So you need to show that T plus I is either one of them. CT is the same as which representative here. Okay, yeah, check. So you need to check. So for example, okay, so this is a very good example to see whether you know the operation in quotient ring or not. So let's check what is this. So let's add two cosets together. So just now we say how to add these two cosets together. We just add up the representative. Okay, but we found that when I add up the representative, I get T. So I get T. Oh, yes, I get T plus T squared minus 1. But just now I claimed that there's only 4 of them, 4 different ones. So T plus T squared minus 1, the ideal generated by T squared minus 1 should be one of them. So which one of them? Which one of them? How to show? Do you know how to show? Know how to show now? Know how to show? T live in which coset actually? Sorry? 1 plus T? Sorry? 1 plus T. Say again? Here. T live in the same coset as 1, you mean? How do you show it? How do you show it? How to show something living in the same coset? Remember the theorem last time? Okay. How to show that AH equals to BH? How to show that AH equals to BH? If what? If B inverse A is in H, then AH equal to BH. Is it correct? Correct. Okay. So there are 4 representatives here. Okay. Take any element from here. Minus with the representative here. Can you show that it is in the ideal generated by T squared minus H? Minus E. Yeah. T squared minus E, you know. Any idea? If no idea, maybe I'll let you go back and try, and then we will discuss next class for this question. I still have, let me see, 1, 2, 3, 4, 5, 6. 6 slides. I'll finish today. Okay. So maybe go back and think. Which does this which this coset equals to? Okay. Is equivalent to which coset? Okay, try and do this. Okay, I will put it into the lecture notes. Okay. Yeah, let's continue. Let's finish it. So next theorem is if I have a position, so I have a ring. Okay, let's look at a ring. And I have an ideal generated by a few elements here. Okay. Ideal. Where all these AI is in R. Okay. How do I compute R, the quotient ring of R by I? Okay, how do I compute this? Actually, what can I do is I can quotient it one by one. I can quotient it one by one. Okay, I can quotient it like this. Okay, I can quotient it by A1 first. The principal ideal generated by A1, and then I quotient it by principal ideal generated by A2 again. Okay. And then I can do it inductionally by one. Okay. I can do like this. Okay, so what does this mean? This is like number. This is like number. You want to take 100 divide by how much? Maybe 8. How do you divide? You can straight away divide. Or you can divide by 2 first, and you divide by 4. Or you can divide by 2, divide by 2, and divide by 2 again. Okay. So this is the same as quotienting with the ideal generated by the union of different number of elements. Okay, so you also can do this. You also can quotient by 2 elements first, okay, and then quotient the rest, and so on. Okay. And then there's a proof of this. Huh? Sorry? Number line. One number line. Okay or not? Okay. So you meaning I can change the order where I take the quotient. Right. So for example, in the number, right, if you want to divide by 6, you can divide by 3 first and then divide by 2. Or you can divide by 2 first or divide by 3. So similar here. Okay, if you have an ideal generated by n elements, you can divide by the principal ideal, okay, generated by either one of the elements first, okay, or ideal generated by 2 of them, 3 of them first, and then divide the rest, quotient by the rest. Okay, can get it? One last example and then we can leave. Okay, so one last example here. So how do we use this proposition here? Okay, how do we use this? So let's try and identify this ring here. Zi over I minus 2. Okay, Zi over I minus 2. What is this ring here? Sorry. Zi quotient by I minus 2. Yeah, Zi quotient by I minus 2. Do you know what's this ring here? Sorry. Zi is the Gauss integer. Okay. And then I quotient out by this I minus 2 here. So meaning multiple of I minus 2 is the equivalent class of the identity. Okay, identity concept. How about the other elements? Okay, turns out that there are 5 elements inside here. Yeah, there are 5 elements inside here. So how do we see this? Okay, how do we see this? So let's take another approach. So step A, okay, we can define the map. like this. Okay. So how do we get I? So how do we get I here? So I just send the X to I. Okay. What's the kernel here? What's the kernel here? What does I have to satisfy? X squared equals to -1. So what's the kernel here? I squared F2 equals to -1. Meaning what? I squared plus 1 equals to 0. Why is the thing get sent to I squared plus 1? S squared plus 1. Okay, so this is the smallest polynomial. S squared plus 1. Or you can use division with remainder to prove this because Zx is no longer a polynomial ring over field. Okay, I don't know whether it's principal or not, but you can use the division with remainder to prove it. So by first isomorphism theorem tells you what? Is this a surjective map or not? Is this a surjective map? Yes, right. Because I already tell you where this generator I, where's the pre-image of I. For coefficient, it just get fixed. Okay, get fixed. So Zx quotient by this kernel is what Zi is. Okay, so this is how we get complex number actually. Complex number is what? Ri, because A plus Bi, right? So you can map a polynomial ring Rx to Ri, sending X to I. So, okay, so aside here. So if I change this Z to R, what we get is Rx quotient by X squared plus 1, which is isomorphic to Ri, which is equal to C. Okay, so this is exactly how we build C. We call C an algebraically closed. Why? Because this is the only algebraic equation that don't have root in R. I mean, the ideal generated by this guy. Okay. So once we add the I in, all the polynomial will have roots in C. This is what we call the fundamental theorem of algebra. Okay, no? So in this way, C is algebraically closed. Okay. So I, what is I? I squared equals to -1. But for algebra like us, we prefer something equal to 0. So we look at I squared plus 1 equals to 0. This is the equation we see. Okay. All right. And then what else? And then let me see. So our goal is to look at this quotient, right? Okay. So what's the pre-image of I minus 2 under phi? Let me put it here. And make this smaller this size. So what's the pre-image of I minus 2? It is just X minus 2. Okay. So by the proposition above, okay, how do we use it? How do we use the proposition above? So we have Zx. We can take quotient by X squared plus 1 quotient X minus 2. Okay. We can choose either one to quotient first. Okay. In particular, we can choose S squared plus 1 first. And then I quotient X minus 2 later. In this way, I will get Zi quotient by I minus 2. Okay, because X minus 2 in the new ring become I minus 2. Makes sense or not? Okay. 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 Makes sense? Okay. So to be precise, right? I think we should put some bar at the top here, right? We should put some bar at the top. Yeah, put some bar. Okay. All right. So what's this? What is this? But we can go the other way. We can go the other way, right? We can go the other way. We can instead divide by x minus 2 first. Okay. If I divide by x minus 2, what does it mean? I send my x to 2. Real. Okay, so let me take this out. So what is zx over x minus 2 means? This means what? What map has kernel x minus 2? What map has kernel x minus 2? How to understand this? I need first isomorphism theorem, right? I need a surjective map. Okay. I need a surjective map P from Zx to something that has kernel P equals to x minus 2. So that I have an isomorphism here. What's the map should be? Send x to 2. Very good. But the image is just Z. Is the isomorphism here. Is it an isomorphism or not? Because the pre-image of Z is just Z. Z is a coefficient in Zx. Or you see Z as a constant polynomial. Right. Okay. So meaning what? The first quotient here is just isomorphic to what? Zx over x minus 2. Isomorphic to this isomorphism here. Isomorphic to Z mod 3. Where is the Z mod 3? I mean, this image, the image of this surjective map is Z, right? So by first isomorphism theorem, you get Z. Okay. But the residue of s squared plus 1 here become 5. X I sent to 2 already. Okay, so it become 2 squared plus 1. So I should write 2 squared plus 1. And then this thing is just equals to Z quotient by the ideal generated by 5. And then what is this? This is what? 0 is equal to 5, equals to 10, equals to minus 5. So this is exactly Z 5, Z mod 5, correct? Yes, Z mod 5. Okay. So if you go the other way, it's easy to see there's only 5 things here. So I challenge you, go back and write down the 5 coset. Yeah. Go and write it down. Why is the 5 coset here? Because in one way, I tell you there's only 5 things here. The other way, this is a coset. So what's the 5 thing? 5 coset here. Go and write it down. I will write it down for you also. You can trace it back using this isomorphism, or you can go and try to compute it. Yeah. You can use this line to go back because isomorphism, right? So you take 1 here. Okay, you take a 1 here, and then you trace back this isomorphism. So where the 1 should go? And not quite just isomorphism. You just use isomorphism. Okay? Because Z5, there are 5 elements. Okay, you can go through, because the isomorphism, right? You can go back and forward. So you can go from Z5 all the way back to Zi over I minus 2. Find the 5 coset. Okay, no? Go and find the 5 coset to convince yourself Zi over I minus 2, there's really only 5 things there. Make sense? Okay, because this is a chain of isomorphism. This isomorphism, actually, I didn't tell you. It is in the proof of the proposition just now. So you need to figure out what's the isomorphism we need to use inside here. Then you will know what the map is. Okay, Okay, no. I didn't tell you the isomorphism. The isomorphism is exactly inside this proof. So you need to know this proof to know the isomorphism. If not, you just need to try and find the 5 representative. Okay or not? Any question before we break? Yeah. Any question before we break? No? Okay, if not, you are welcome to watch Jimbo later in the where is it? A3618. Okay, from 6 to 8. Okay, we'll see you next week.
我去，我去对面。